And welcome again. This time we have a rotating dipole. Well, an electric dipole is made of two particles with the same mass m. The particles are attached to the ends of a rigid weightless rod of length L. That's right. They have electric charges plus q and minus q. This dipole is rotating with an angular velocity omega. Omega is provided in the picture. So, angular velocity in the horizontal plane around the vertical axis that passes through the dipole center O is as in figure. At some time, a vertical magnetic field B is turned on sometime. So it was first rotating about the vertical axis passing through O. That is the horizontal vertical axis. Yeah. And since it was initially placed in horizontal plane, so an axis perpendicular to the rod will be of course vertical. At some time a vertical magnetic field is turned on. Describe the steady state motion of the dipole. So that means we have to consider things when the magnetic field is turned on. I guess each particle will be affected by the Lorentz force itself, magnetic force, QPB in this case. And I've drawn a picture for this, for describing all the conditions. So I would like to minimize this picture. And then bring the other picture in the frame. Magnetic field, the direction of magnetic field I have taken in vertically downward direction, and charges, since the charges were rotating in this manner, so I provided a velocity v to this minus q charge and velocity b to this plus q charge, and the force acting on this charge, the Lorentz force, will be this. Definitely you can find the direction with right hand screw rule, and on this charge the Lorentz force is in this direction, and the magnitude of the force will be QBB simply. B and B are perpendicular to each other, so their planes are perpendicular, they must be perpendicular, and V can be written as simply as omega L by 2. So magnetic force is basically Q omega L by 2B, and you can see that a resultant force acting on the dipole due to this Lorentz force, two Lorentz forces are in same direction. So the resultant force acting on the dipole is 2FL, twice of the Lorentz force. That will be simply Q omega LB. And the value of this force is constant, but its direction continuously changes. Basically, the resultant of these two forces, vector F, rotates with the rod with angular velocity omega. Of course, this net force F, the resultant of these two Lorentz forces, it will keep rotating with the rod with the same angular velocity omega. But, but because it cannot produce itself any rotating action, because it's already passing through the center of the dipole center. But that means the dipole center will also revolve with the same angular velocity omega. And what will be the radius? Because I don't know what will be. I'm sure for one thing, the dipole center will also revolve with the same angular velocity omega. Suppose along a circle of radius r, which can be determined if we don't know, by simply using Newton's second law of motion, because the resultant force responsible for this is simply F. So this F will be equal to mva square, or total mass is 2m, and it's rotating with angular velocity omega, and we don't know the radius. So it can be Newton's second law of motion provides us equation like this, and we find the value of r equal to F by 2m omega square, everything given, and we can write the value as QLB upon 2 omega. That means we found the solution perhaps. The problem was describe the motion. The problem was to describe the steady state motion of the dipole. Of course, this is rotating in a circle with the dipole center is rotating in a circle of radius this, and this can be the answer. Thank you very much for watching now.